In this lesson, we're going to take what we had already been working with previously with areas between curves, and we're now going to start revolving these to form 3D shapes and getting what we call volumes of revolution. We're going to look at two different methods, the disk method and the washer method, and we'll break it down and look at examples of each one. Now we're going to look at a typical disk problem. They'll be worded something like this. Find the volume when the area bounded by y equals x squared, y equals 0, and x equals 3 is revolved about the x-axis. So let's start by first of all graphing our functions. Y equals x squared, we've got our parabola. Y equals 0, which is the x-axis. And then x equals 3, which is going to be a vertical line. So we're talking about taking that shape and we're going to revolve it around the x-axis, and when we do that, we're going to have a 3D shape. So if I kind of sketch my revolution, we'll just kind of dot that. It's going to look something like that. So what happens is, what we have here is a disk method problem. So if I look at this, going back to our idea of our rectangles, imagine taking a rectangle that would be a dx. Let's make that a little bit darker. Okay. So imagine taking a dx rectangle like that. And we're also going to spin that rectangle. Well, when I do, what's going to happen is we're actually going to get a little cylinder. So it would look, that one rectangle would sort of look like that, so that I have a cylinder here, or a solid disc, a solid cylinder. Alright. So what we do is, to find our volume, I find, first of all, the volume of that, and think about doing a bunch of those of different sizes, and we'll look at a graphic here in a minute to kind of give you an idea of what we're talking about. But I would do a bunch of those, and the volume of that total would give me the volume of my entire area, or my entire 3D shape. So what we'll do is we'll find the volume of that. Well, that happens to be a cylinder, and the volume of a cylinder is pi r squared h. Now here again, like our area, is the problem we need to think about with h. That is your height of your cylinder. That's going to vary depending on how thick you make your rectangles. So that's going to be our dx or our dy. So your height will always be whether the problem is dx or dy. So really what we're going to do is we're going to work on just using pi r squared. So to find the volume, we're going to do an integral. We're going to do pi times the radius squared, and then times the height, which in this case is going to be a dx. Well, the radius of my rectangle, or not my rectangle, but of my cylinder, is actually going to be this distance here. Because if I look at that cylinder, the radius would go from here to there. Alright, so then we're looking at that distance being my radius. Well, it's a dx problem. We want to do top minus bottom. The top of the radius would be x squared. The bottom of the radius would be, the axis would be 0. Then I do my limits of integration. Since this is a dx problem, we want to start finding the volume there, which is at 0. And we want to stop when we get out to here, which was at x equals 3. That was my boundary. So that would be my integral that would find the volume. Now, to give you a little better graphic of what we're doing here, let's look at, here is y equals x squared, just like we were looking at in the previous problem. Now, they did it at x equals 2 instead of x equals 3, and you can kind of see that you've got several different discs drawn in here. So to kind of give you a better graphic of what was happening, I've got all those discs. We were revolving around the x-axis, so I've got all of those discs that I'm going to find the volume for. And if you'll notice, here was our formula that we talked about, that to get the volume, we do area times thickness. The area of our shape was a circle, because we said that this was a cylinder, so we do pi r squared h. So if I do the disk method, what I want to do is to find the volume. I want to integrate from A to B, and then I'm going to have a pi, and I normally put the pi's out in the front, so let's go ahead and move that. And we'll put our pi out in the front of the integral. And then I'm going to have my radius squared, and then dx or dy. And if my problem is a dx, then to get the radius, I'm going to do top minus bottom. If my problem is a dy, and I have the integral from a to b, radius squared dy, then to fill that in, I'm going to do right minus left. And we'll look at several examples of those here in just a minute. So let's look at a disk method problem that actually turns out to be a dy this time. Alright, so we have find the volume when the area bounded by x equals 2 minus y squared. So I just took some time, plotted the points there. X equals 0, which is your y-axis, is revolved around the y-axis. So let's kind of visualize that what's going to happen is I'm going to spin that around there. Now, because my shape is kind of on its side, my parabola is x equals 2 minus y squared, then what's going to happen is when I draw in my rectangles, they're going to get drawn in on their side. So that's going to be the rectangle that we're revolving to make our disk. So it still relates back to our area problems. And that rectangle is going to revolve, and it's actually going to form a cylinder. So if I looked at that alone, I would see something like this. So I've got a little short cylinder. So to find the volume, I'm going to do an integral, and it's going to be pi radius squared, and this time it's a dy. Now I have a couple options for my limits of integration. If I look at the equation 2 minus y squared, I'm going to, since it's a dy problem, I need to know the 2 points where I touch the y-axis. So I'm looking for this point and this point, which is really the zeros to 2 minus y squared. Well, if I solve that, I'm going to get that y is plus and minus the square root of 2. Okay, so this would be the point 0 square root of 2, and down here would be 0 negative square root of 2. So then I have the option of doing my limits of integration from negative square root of 2 to positive square root of 2. And then if I do right minus left, now remember it's all about my original graph. The right would be 2 minus y squared, because the original rectangle was right here. And then the left would be the axis, which is 0. Now one other thing that I could do that would make this a little easier, especially if I've got to integrate. Let's clear off some room here. If I'm doing it and just setting it up, it really doesn't matter if I don't have to integrate the problem, what my limits of integration are, as long as I do as a dy. But if you have to integrate, you could actually do this a little easier and say, hey, why don't we just worry about finding this top part of the volume and then doubling that. So if I could find that, then I could double it and get the total volume. So then I could do, instead of from negative square root of 2 to positive square root of 2, I could do from 0 to the square root of 2 and then just double that and still keep my same radius, and it's still a dy problem. So that's a little quicker if you have to actually integrate, because it's much easier to substitute in 0 than negative square root of 2. The next thing we're going to focus on is the washer method. Now, when you have the washer method, what's going to happen? Let me just kind of sketch something out here, kind of like this one, let's say. Let's say we had y equals x squared and y equals x. That would give you a graph that looked like that. And let's say I was going to spin that around the y-axis. So there's kind of my revolution. What's going to happen is when I draw my rectangle and revolve that rectangle, there's going to end up being a gap between the axis of revolution and my rectangle. So when that happens, my shape, my graphics are not going to be really good here, is actually going to look more like a cylinder or a donut with a hole in the middle, a washer. So much better picture here, or here if it's a DY. So that's what your shape is going to look like. So to get my volume, what I'm going to do is I'm going to think of this as another cylinder with a hole in the middle of it. Well, to get the volume of the cylinder, it's actually a cylinder minus another cylinder. To get the volume, I'm going to do an integral. But this time, to find the area of my, or the volume, I should say, of that cylinder, I'm going to have to take the big cylinder, which is pi, and we'll put big R squared, H, minus the little cylinder, which would be pi, little r squared, H. Now, let's go back and take this off before we do anything else. Let's see if we, there we go. So I'm going to kind of just work with that for just a minute. Notice that both of these have a pi and an H. So I'm going to factor out a pi and an H, and when I do, I get big R squared minus little r squared. Okay, now just like before when we did this, our H was our height, which is whether it's going to be a dx or a dy. So you'd really want to think of this as being pi, big R squared minus little r squared, and then H on the end. So to find your volume, let's try to get us an integral now. So to find the volume, we're going to do volume equals pi integral from A to B, and then it's going to be big radius squared minus little radius squared, and then it's either going to be a dx or a dy. Now you're still going to do top minus bottom if it's a dx, and you're going to do right minus left if it's a dy. We'll look at a couple examples of those next. Alright, so here's going to be a washer problem. You want to find the volume when the area bounded by y equals 2x plus 1 and y equals 7 minus x equals 0, or the y-axis, is revolved about the x-axis. So I've taken some time, I've plotted a few points, and then I've gone ahead and kind of drawn what the reflection would look like. Alright, so what's going to happen is when I draw in my rectangles, I'm going to draw my rectangles this way as dx problems. And notice that there is a gap between my rectangle and my axis of revolution because we're going about the x-axis, so I'm revolving around this line. So then that tells me that this is a washer problem. So to find the volume, I do the integral. Now looking at my graph here, I'm going to go from 0 to, it appears these are intersecting right here when x is 2. Alright, and then I'd want to do big radius squared minus little radius squared, and it is a dx problem, so it'll be dx. Now this is the part you have to be very careful about. To get your big radius, and let me kind of sketch this in for us, the big radius always goes from the axis of revolution to the curve farthest away from it, so it'll be up to here. And then you want to do top minus bottom. The top is your line, 7 minus x, minus the bottom, which would be 0. To get the little radius, your little radius goes from, same thing, axis of revolution to the closest curve, and you do top minus bottom. So in this case, the top would be the line 2x plus 1 minus the bottom, which would be the axis, which would be 0. Now notice that if you had to integrate this by hand, it could get to be a real pain because you probably are going to have to square these out, integrate them, and then evaluate them at 2 and 0. Alright, we're going to look at one last problem, and what we're going to do here is we want to find the volume when the area bounded by y equals 2x, which is my orangish mustard color line here. So y equals 2x, and the line y equals x plus 2, which is my line here. So those are my boundaries, along with the y-axis, okay, which would be here. So it's this little triangle shape here. And that's going to get revolved about two different places. One's the x-axis, one's the y-axis. So we want to look at both of those. Let's start with x-axis first. Okay, so if I do the x-axis, let me just kind of sketch in what the revolution would look like. Okay, it looks something like that. And then what we're going to do is we're going to draw in our rectangle. But our rectangle we're going to draw, since it's going around the dx, or the x-axis is a dx problem. Okay. On disc and washers, that's one way you can tell. If it's around the x-axis, it's a dx problem. If it's around the y-axis, it's a dy problem. Or you want to try to make it that kind of problem. We'll talk about later that you can actually change that around a little bit. But on disc and washers, x-axis is dx, y-axis is dy. Okay, so around the x-axis I can tell that it's going to be a washer problem. So we'll just do that part here. That's going to be pi integral big radius squared minus little radius squared, and we said it'd be a dx. Okay, my limits of integration would be from 0 to, it appears, those are intersecting at about the point, or at 2, 4. So it'd be 0 to 2, since it's a dx problem. I want the x numbers. And then I'm going to do big radius, which is axis of revolution. Let's try to draw this in for us so we can see it. This picture's getting a little messy. But axis of revolution to the farthest curve away, top minus bottom. Well, that would be the line x plus 2 minus 0. And then the little radius would be, color, axis of revolution to the inside curve, or closest curve, top minus bottom, but that would be 2x minus 0. Now, to do the y-axis, and we're going to switch to another screen so we can get a little better idea and diagram here of what's going on. Alright, so we're looking at this area again. So we're taking this, and we're going to spin it this time around the y-axis. So again, just to kind of give us an idea, your revolution is going to look something like that. Now, because I'm going around, this is our B part, we're going around the y-axis, then it needs to be a dy problem for right now, because that's the only way we know how to do it. We will talk about another method later. If I do it as a dy, here's where it gets to be a little messy, because that rectangle has a different left and right than that rectangle. So what I'm going to have to do is I'm going to have to split this up, because as it turns out, the bottom part of this, from 0 to 2, that part is all disc. Then the top part of it, if I go from 2 to 4, let's do that in a different color, that part is going to end up being a washer. So I'm going to have to do it in two separate integrals. One for the disc, one for the washer. It's kind of a mess, but you hopefully can get the idea. So, we're going to find our volume by doing, let's do the disc part first. Okay, remember my lines were y equals 2x and y equals x plus 2. Okay, if I do it as a disc problem, there's going to be my rectangle. So I'm going to have pi integral, and it's a dy. So my limits of integration will end up being 0 to 2. And then it's going to be just radius squared. Well, the radius would be right minus left. The right would be on the line, 2x, but this has to be a dy problem, so we solve for x and get y over 2. So it'd be y over 2 minus 0. Again, you don't have to put the minus 0 in there. And then it's, since it's a disc, it's pi radius squared, dy. Then we're going to have to add on the part that's going to be a washer, which that's going to be pi integral, and this will go from 2 to 4, And now I've got to do big radius squared minus little radius squared, dy. Okay, let's try to draw these in. Big radius is going to go from axis of revolution to the curve farthest away from you and do right minus left. Well, that would be my y over 2 minus 0. And then the little radius is going to go from axis of revolution to the curve closest to you, or to it. And then I'm going to do right minus left. And again, I'll need to take this equation and solve for x equals, and I would get y minus 2. So the right would be y minus 2 minus the left, which is the axis, which would be 0. So it'd actually take both of those integrals to find that volume. Later on, we're going to talk about something called the shell method that would allow us to do that as a dx problem and would allow us to do it with one integral.